This is Mr. Martin. These are the video notes for section 6.1 continued and 6.2 for Geometry Advanced. We're going to continue talking about circles and the different properties of circles. There's a lot of information in these couple of sections in this chapter in general, so make sure you're keeping up on the homework and getting help when you need it. So probably in class we at least got to talk about the tangent conjecture, and we were saying that anytime you have a tangent to a circle, it's a good idea to mark in those right angles in there, because then we can use that to help us solve other problems. Again, if you have questions about that, make sure that you ask. And then we may have also started to talk about the tangent segments conjecture. So tangent segments to a circle drawn from a single point outside a circle are, and then we were getting to talk about that. So we know what a tangent is. It's a line, and I have a line here that goes through A and N. I just didn't continue it past N. And I have another tangent over here that goes through N and G. Again, I didn't continue it past N, but I could have if I wanted to. And then since they're tangents based on the previous theorem, again, we want to mark these with right angles. And when we talk about tangent segments, we've got this single point outside the circle, point N. And if I connect this point outside the circle to the two spots on the circle where it could be tangent, so it can be tangent at A, and I can draw a segment from N through G, and it can be tangent to the circle at G, I get these two segments, and we call them tangent segments. So NA and NG are what we call tangent segments. So when we do this, tangent segments drawn to a circle from a single point outside a circle. So this single point outside the circle, this is point N. Alright, and then the tangent segments that we're talking about are segment NA and segment NG. So what ends up happening is that these two tangent segments become congruent. So now I've got that NA and NG are congruent. So just like we did with our previous conjecture, we want to mark things that we know. So anytime you have tangent segments drawn from a single point outside a circle, it is a good idea to mark them congruent. Okay, so anytime we see a radius to the point of tangency, we're going to mark it with a right angle. Anytime I see tangent segments to a circle, we're going to mark those congruent. Okay, so let's go ahead and let's apply these conjectures. So for the first example, we want to determine if line AB is tangent to the circle. So if AB is tangent to the circle, then we would know that this would be a right angle, which means that this triangle would be a right triangle. So if A squared plus B squared is equal to C squared, then AB is tangent. Okay, so if I can show that this is a right triangle, then this will be a right angle, which means that AB would be tangent. So this is the angle that would be our right angle here at A. So these would be the two legs if this is a right triangle. So what I want to do, if you remember from our triangle inequality conjecture, I want to look at 1.2 squared plus 1.6 squared, and I want to look at 2 squared. And I'm going to compare these two answers, and if they happen to be equal, then this would be a right triangle, which would make a right angle, which would make AB tangent to the circle. So 1.2 squared plus 1.6 squared, that comes out to be 4, and 2 squared is also 4. So since A squared plus B squared is equal to C squared, the triangle is a right triangle, and AB is tangent to the circle. Alright, and again, if you have any questions about that reasoning, make sure that you ask. Okay, so again, if this is tangent, we're going to have a right angle here. If that's a right angle, then in this triangle, the 8 and the 5 would be the legs. So I'm going to compare 5 squared and 8 squared. That comes out to be 89, and I want to compare that to 10 squared. That's 100. So in this case, since a squared plus b squared does not equal c squared, angle A is not a right angle, and AB is not tangent. Alright. Moving on to the next example, so let's use our other conjecture, our tangent segments conjecture. So solve for x, assume that lines which appear to be tangent are tangent. Alright, so this line appears to be tangent, and this is my point of tangency, so this is going to be a right angle. And this is a point of tangency, so this is going to be a right angle. And I have two tangent segments here, one over there and one over there, so I know that those are going to be congruent because they're tangent segments from the same point outside the circle. So if these two tangent segments are congruent, that means that my 5x plus 5 is going to equal my 7x minus 1. So I have 5x plus 5 is equal to 7x minus 1. I'm going to subtract 7x from both sides, so I get negative 2x plus 5 is equal to negative 1. I'm going to subtract 5 from both sides, so I get negative 2x is equal to negative 6. Divide both sides by negative 2, and I get that x is equal to 3. Okay, so if you want to check to make sure you did this right, just go ahead and either do it in your head or write it out. Plug 3 in for x, so we would get 15 plus 5 is 20, and here I would get 21 minus 1, which is also 20. So you can check. Alright, moving on. Again, I have a tangent segment over here, so we know that this is going to be a right angle. Tangent segment over there, this is going to be a right angle. Two tangent segments from the same external point. These are going to be congruent. We've got some extraneous information here. We don't really need this. Don't need. Just some extra information. So since these two tangent segments are going to be congruent, I can set them equal to each other. So 3x minus 2 is equal to x plus 2. Subtract x from both sides, I get 2x minus 2 is equal to 2. Add 2 to both sides, 2x is equal to 4. Divide by 2, and I get x is equal to 2. So again, pause and rewind as needed. Make sure you write down questions so that you can ask them. Or if you happen to be watching in class, make sure you ask me right away. Alright, moving on. Again, lots of information in this these sections, so make sure that you stay on top of it and ask questions. So we're going to talk about the distance from the center of a circle to a chord. So it's the measure of the perpendicular segment from the center to the chord. So in this case, in our picture, segment AE represents the distance from the center to the chord. Alright, so keep in mind that this smaller segment here, AE, is really the distance from the center to the chord, but I also have a radius, AB, that's associated with it. So keep that in mind. Anytime I have a distance to a chord, I also have a radius associated with this. Alright, and then again, we want to remember our Pythagorean theorem. How does this apply? Well, we can draw in some right triangles over here and over here, or we could draw some right triangles over here and over here. So we end up having a couple different pairs of right triangles that eventually we're going to use the Pythagorean theorem to help us solve for either the radius or the chord or the distance from the center to the chord. So keep that in mind. Alright, so we have perpendicular to a chord conjecture. if a radius is perpendicular to a chord, then, so if I have this radius, AB, and it's perpendicular to the chord, well, what do you think it does to the chord? It looks like it may divide it in half, and in fact it does. Then it bisects the chord. Okay, so the information that we would be given is in the hypothesis of our statement. That's the if statement. So if we were given that AB is perpendicular to DC, so the radius is perpendicular to the chord, the conclusion that we could make is that AB bisects DC. Okay? And then after that, we could also conclude that DE was congruent to CE. Okay? And a lot of times when we do algebra type problems, we're going to make that leap from being perpendicular to having those two congruent segments. Alright, moving on to our next conjecture, we've got perpendicular bisector of a chord. So the perpendicular of a bisector of a chord passes through, so you can see if this is perpendicular and it also bisects it, so since BA is the perpendicular bisector of a chord, we see it passes right through the center of the circle. Okay, so what we might be given is that BA is the perpendicular bisector of PQ, segment PQ, therefore segment BA passes through the center. Alright, and then we'll look at some examples, or actually we'll look at one example in these notes of how to use that. Moving on, two more we have here. Chord distance to center conjecture. If two chords of a circle are congruent, so in this case the two chords of the circle that would be congruent would be AB congruent to CD, then they are, so if these two chords are congruent, we can kind of see that it looks like it's about the same distance from the center, so we would say that they are equidistant from the center of the circle. So what that would mean is that if we were given that AB is congruent to CD, when we see this word equidistant, what we want to do is we want to think I have congruent segments. Okay, so we say equidistant, but really what we're looking for are congruent segments. That's what you want to think about. So if the two chords are congruent, then my conclusion would be that XP is congruent to YP. Alright, and then this is how we show equidistance. Okay, so it's a big fancy word. It really just means equal distances or congruent segments. So keep that in mind. Alright, and then the chord distance to center conjecture is really just the converse. If two chords of a circle are equidistant from the center, so now we're starting out with PX congruent to PY, then they are congruent. So in this case, we would be given AB congruent to, we would be given XP congruent to YP, because again we're talking about the converse now, so now we're starting out with the distances congruent. Then, so we've got AB congruent to CD. Okay, and again, you're going to have to get a bit of practice in for this in order to, you know, learn these. So make sure you're getting the practice in. Why don't you go ahead and try these examples, and we will talk about them in class. And if you have any questions, make sure that you ask.